I got this document here. Where do we want to begin?
Good. Let's see. Let me just pull up the assignments. Page 110, number 1, 4, and 5. 7,
Okay.
8, 10. Yeah. We'll just start with 1.
Why is 0 not in the domain of y equal k over x or y equal k over x squared?
Why is 0? I don't know. I'm not sure.
If I say, what is the domain of this function, what is the domain?
It would be x, whatever x is.
Whatever x can be
Right.
is what the definition of domain is. And what can x be in this one that I've written here?
Oh, well, I guess it can be anything but 0 since it's a fraction.
Exactly. So that's the answer. Why 0? Because you can't divide by 0 is really the answer to number 1.
All right.
And the fact that there's a k doesn't really matter. The key part is that the x is in the denominator, and that's what you can't divide by. So number 4. State the domain and range of this function, f of x equals 15 over x. What's the domain of it?
I mean, it would be whatever x is, right?
Remember what domain was in the last question.
Yeah, it can be anything but 0.
Okay. So you might, do they use interval notation in your class? In other words, how would they answer? How would they answer?
I guess it would be x is equal to or bigger, or bigger or than or equal to 0 or...
This can be one answer, which is all reals except x not equal to 0. That's double R, means all real numbers.
Right.
Another answer would be negative infinity to 0 combined with 0 to positive infinity. This is called interval notation. This is a U in the middle here. Have you had that? Interval notation yet?
No, we normally do the one with the all reals, I think.
Okay. All right. That's simpler, although in some situations there's like 3 different intervals that make up the domain, and it's harder to state with just that. But now let's look at range. Range is what f of x can be.
Well, the range would be 15, wouldn't it?
No. The range is going to be all of the potential values that f of x can attain. If we graph this, maybe it will help, because you can read range and domain right off of a graph.
Right.
Hyperbolic. So we have a horizontal asymptote at y equals 0, and we have a vertical asymptote at x equals 0. So if I'm looking for a domain, I'm going to look along the x-axis, and I can see that, wow, it can go to negative infinity, can go all the way up to 0, can't be 0, but it can go from 0 to positive infinity, going in that direction. So that's the domain. So we can read that off the graph if we can't figure it out algebraically. Well, let's try to do that with the range. Look on the y-axis. In other words, this is f of x, and this is x. So what can f of x do?
Wouldn't it be the same?
Exactly. All reals except y cannot be equal to 0. The reason it can't, if you look at this function, notice that the only way anything can be equal to 0 is if its numerator is 0. So when we put a constant in the numerator, we effectively make it so that y can never be 0.
Okay.
Now, the question is, do you need to be able to draw this graph? You can see from this example that by drawing the graph, I can answer the question a whole lot easier. It wouldn't have been that easy to come up with the range looking at this. I mean, it's obvious to me that it can be anything except 0, but it might not be obvious to people who don't do this 4 hours a day like I do.
Right,
So,
yeah. I mean, usually we can use calculators on things like this, so...
Well, I noticed that most of the beginning of this chapter was all about the graphs.
Right.
So I suspect they want you to be able to look at these graphs. This graph.
Yeah. So I mean, but we're allowed to put in the function in the calculator and see what the graph looks like.
Okay. Okay. Good. And
in most situations.
There is the hyperbolic function right there. In other words, that's what I just drew. All right. So let's go back. It was 1, 4, and 7.
5.
1, 4, and 5, okay?
I believe. Yeah.
Okay. So what is f of minus 10?
What is f of minus? I don't really understand what that means, evaluate. I mean, I understand what it means, but how are you meant to just, what's meant to come out? I don't understand.
Real simple. Substitute whatever is in the parentheses for x.
Okay.
Very straightforward, and you always want to do that.
Okay, so it would just be f of x equals 10, negative 10?
No, f of x is a function, meaning that this is going to have x in it. So f of negative 10 is going to be equal to a certain number. It's going to be equal to whatever this number's results when we plug in minus 10 for x. So it would be 15 over minus 10, which is negative 1.5.
Oh, right. I forgot that we were using the same equation from above.
Right. In other words, this is f of x. So whenever you are given an f of x and then you're asked to evaluate it f at some value, that's all you do is plug it in. So what's f of 15?
So 15 would be, let's see. Oh, it'd just be 1.
What's f of x minus 1?
Minus 1. It can't be that, can it?
Well, I'm just asking. Yeah. Yeah, you can put in whatever you want in there. It's actually a very key point to calculus, is understanding. So what was the rule? Whatever's in the parentheses, substitute for x. And that's the answer.
Okay.
Okay? So what if I said f of x plus h?
Then you would just put 15 over x plus h.
That's it. And that's all you do. So even if they make it more complicated than evaluating it at a number, you still know how to do it. And graph f in the window minus 12. I presume they want you to do that on your calculator?
And sketch the graph, yeah. definitely. Okay, let me pull it out.
Okay.
So,
You know how to set your windows? That's probably why they're asking this question.
yeah, I know how to do it. So I would just type in the equation.
Y equals 15 divided by x.
Okay.
And then go ahead and graph that and see what you get. See what the window is.
Okay, it's the height, or what the two, I forgot what they're called, hyperbole or hyperbole.
Yeah, it's hyperbolic. Right.
Hyperbolic.
In other words, it's going to look just like the hyperboles that I've been drawing. Okay, but they want you to be able to have the end of this be minus 12 and the end of that be plus 12 and this be plus 12 and this be minus 12. So do you know how to do that in your calculator?
I don't think so. Let's see. So 15 divided by x, f equals 15 divided by x.
That's your function, and that should be, you put that in where you're putting in y1, y2, y3.
Right.
You're using a TI-84?
Yeah.
Okay. Now hit graph.
Okay.
Can you read the x-axis scale?
I think I'll have to zoom a little bit.
Well, if instead of zooming, let me pull out my calculator here. Hit format. Format's above the zoom key.
Okay.
And that should let you set the minimum X value. Am I wrong? My calculator's batteries are not working. So I can't actually turn mine on. It's been a while since I've used it. But
Let's see.
the format key, I think, lets you set the dimensions of the graph.
It says rectangle GC, polar GC, coordinate on, coordinate off.
Okay, I got the wrong one then. Window. Hit the graph and then hit the window key.
Okay. Okay, yeah. X min, X
Okay,
max.
so for X min, put minus 12.
Okay.
For X max, put 12.
Right.
For the increment, use 1.
Is that the scale?
Uh-huh.
Okay.
And then do the same for the Y, min and max.
Okay.
And then hit graph again.
Okay. I mean, it looks pretty much the same.
Well, it may be that the default, when you first did it, was very close to this dimensions.
Yeah.
But I think the main point of this exercise is that you know how to go in there and hit window and change the window, the viewing window.
Okay, so should I just draw this graph then?
Yeah, I guess that's what they want you to do. This seems to me like it's strictly a calculator problem. Maybe not. You have to turn this homework in on paper?
Yeah, but this would make sense because I remember doing something like this on our calculators the other day.
Yeah, okay, well, do your best impression of drawing that graph. To me, all hyperbolic graphs tend to look the same. I mean, the only thing that's different is the 15. And the effect of the 15 makes it flatter rather than deeper. But it's hard to see visually.
Okay.
Okay?
Yeah, I just did a quick sketch.
Yeah.
All right, so the next one is 7.
Okay? Suppose k is not equal to 0. Is the graph of the equation symmetric to the y-axis? Well, we just looked at one. We're looking at y equal 15 over x. So that's the same as k over x. Is y equal k over x symmetric with the y-axis? And what that means is, can you do a mirror image flip about the y-axis with this?
Right. Yeah, I think you can.
Well, if I were to do a mirror image flip of this part of it, it would look like this.
Oh.
If it were
Okay.
symmetric with the y-axis, it would look like that. This is symmetric with the origin, but not the x-axis and not the y-axis.
Okay, so
The
first
second
one's
one,
no.
the second one, however, y equals k over x squared, notice that that looks like this. Why is that true? Because x squared is always positive, so y is always going to be positive whether x is negative or positive. So it's no longer a hyperbolic function.
Right.
And it is symmetric about the y-axis.
Okay.
Okay? If I wanted something that looked symmetric about the x-axis, that would be it. Notice that symmetry about the origin is mirror that about the y-axis and then mirror it about the x-axis, and you have what you have when you have symmetry about the origin. In other words, symmetry about the origin is mirrored about x and then about y, both of them.
All right. Next one is 8.
Okay. Well, in which quadrants are the branches of y equals k over x squared if k is positive? This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4.
Okay. Are the branches? What does it mean by branches?
Each one of these things is a branch.
Okay. So then it would be in 1 and 3.
Well, remember it's k over x squared. When I drew k over x squared, it was like that. Well, actually,
right. So 1 and 2.
1 and 2 if k is positive.
Okay.
If k is negative, which ones?
It would be in 3 and 4.
Right. In other words, it's going to look like this if k is negative. Because x squared is still always positive, but if k is negative, then y is always negative.
Right. Okay.
Okay?
Yeah, I get that. The next one is 10.
What are the vertical and horizontal asymptotes of y equal 4 over x? How do you figure the vertical asymptote? Without graphing.
What is an asymptote again?
It's a line by which the function approaches but never reaches.
Oh, okay, right.
In other words, if this was the graph, that is asymptotic with the y-axis, and it's also asymptotic with the x-axis. Meaning that as x goes to infinity, this thing gets closer and closer to 0, but it never touches 0. And the same
Okay.
thing is as x goes to infinity, as y goes to infinity, x gets closer and closer to 0, but never touches 0 because you can't divide by x.
Okay.
Why
does it never touch the graph?
Well, because x can never be 0, because you can't divide by 0. And notice that y can never be 0 because the numerator is 4. So you have a horizontal asymptote, which is defined as y equals 0. And you have a vertical asymptote that is defined as x equals 0. Notice that the y-axis is the line x equals 0. And the x-axis is the line y equals 0. A lot of people get that confused and they want to call this vertical one y equals 0 because it's the y-axis. But not correct.
Okay.
Okay?
So do you think I should just draw a graph for that, or?
No, it says identify the asymptotes, and the asymptotes are y equals 0 and x equals 0.
Okay. All right. The next one is
just for if this was the equation instead of 4 over x, what's the vertical asymptote?
it would be x is less than 0, I guess, or
whatever the vertical asymptote is, whatever makes this thing 0.
Oh, okay, then it would be 1, I guess.
So there's the vertical asymptote. Horizontal asymptote is still y equals 0 because it's still the y-axis. So the graph of this thing would be and look like this.
Okay.
In other words, it's always, the branches are always going to be asymptotic to your asymptotes, wherever they are. So far in our example, the vertical asymptote has always been x equals 0 in all three of these pictures here. But in this case here, the vertical asymptote is x equal 1 because that's what makes the denominator 0.
All right. Next one is 14.
Okay. So the Lever law is D equals K over W, where D is the distance from the pivot, W is the weight, and K is a constant of variation. Find K.
Find K. And write a variation equation.
So D is the distance from the pivot. What's that equal to?
5.
W equals the weight. What's that equal to?
That is 120.
Solve that equation for K.
So it's 5 times 120.
So K is equal to 600. So we solved for K. Now if we wanted the specific equation for this seesaw, it would be D equals 600 over W. For that
Okay.
particular seesaw, once you solve for K, now you go back and you write the specific equation. This is a general equation, D equals K over W. That's the general equation for all levers, all seesaws.
Okay.
But for this particular seesaw, its K is probably different than another seesaw that maybe is 50 feet long or something. But for this particular seesaw, this is the equation that governs it. So they're going to give us some other stuff. Okay, good. So part B says make a table of 10 different weights and their distances from the pivot that would balance Quentin.
Make a table. Okay.
In other words, if I had a weight at this point right here, also 5 feet, also weighing 120 pounds, that would balance them, right?
Yep.
Well, what if I had a weight 2.5 feet away, right here? How much do you think would be required to balance Quentin?
2.5.
Half the distance.
Right. So it would have to be. I guess would it be half the weight?
Think about that for a moment from your childhood on a seesaw.
It'd be two. It'd be more. It'd be 2 times more the weight, or 2.5 times more.
2 exactly, because 2.5 is half of 5, so the weight has to be double.
Okay.
And let's go back to the specific equation. There's the equation that we have to solve. So one distance was 2.5 equals 600 divided by W, and if you solve for W, you get 240. So by making up various distances, you can figure out 10 different weights and distances, all from this specific equation. Let me give you a test. If it was 3 feet, what does he have to weigh?
If it was 3 feet, has to be 3 times more.
No. Fill in, use that equation, D equals 600 over W.
Right. So then it'd be 3 equals 600 over.
What does W have to be for 600 over W to be equal to 3?
I completely forget how to do this. That's good.
Multiply both sides by W.
Yeah, right.
And then divide both sides by 3.
Okay.
So W equals 200.
Okay. Oh, yeah.
Okay. Now notice what's going on here. If we take the distance from the pivot times the weight, it's always 600. That's K. In other words, if I was 6 feet away, what would the weight have to be?
It would be 6 equals 600.
Whatever this weight is,
It'd
times
100.
Right. So to come up with 10 different weights and distances is really, you get how to do it?
Yeah, that's kind of silly, but yeah, I get it.
It is silly to have to come up with 10 of them. Coming up with 2 or 3 would have made sense, but what they hope that by the time you do 10 of them, you'll realize that that times that's equal to 600 in every case.
Right.
And that's what they're wanting you to see. Okay, plot
Okay.
your values from part B. What is this table we're looking at here? Is that for a different question? Yeah, it is. Okay. By plotting your values from part B, let's just show you what they mean. If I make a table of 10 different values, and I have a distance and a weight. Well, we realized that 2.5 feet had to be twice as much. 6 feet was 100. 5 feet was 120. 3 feet was 200. So all I'm doing is listing the distances and making sure that the distance times the weight adds to 600. So 4 feet must be 150. You want to come up with numbers that 10 feet would be 60, 15 feet would be 40, 20 feet would be 30, and 30 feet would be 20. In other words, the product of distance times weight has to equal 600, and that's the table.
Okay.
Only you would have 10 different distances and 10 different weights here. I don't think I have 10. I have 9. Let's look at D. Is the domain for the context discrete? Explain why or why not.
Is I'm not really sure what it means by discrete.
Well, it's an unusual question. I think 95% sure that they mean, is it a whole number? In other words, do my distances from the pivot have to be whole numbers?
No.
No, we used 2.5. It worked just fine.
Right.
So I can pick any number I want on the number line. I could have picked 2.19874. If it was discrete, I would only be able to pick 1, 2, 3, 4, or 5, I believe. However, they probably have an explanation of what they mean by discrete earlier in this. Let's see if we can find it. Discrete mathematics is the branch of mathematics that deals with whole number integers. A discrete set is one in which there is a positive distance greater than some fixed amount between any two elements of the set. Okay, in this example, the function has a discrete domain, the set of positive integers. So in that particular problem, W could only take on whole number because it was the number of workers. So if your x-axis is something like the number of people, and people can only come in whole persons, you can't have 1.5 persons, then that is a discrete domain.
Right.
So in our problem, it was not a discrete domain because we could have fractions.
Okay.
What next? What did we just do? 14? Yeah.
Yeah, 14. Next one is 15.
Okay. Boy, they're going to do these hyperbolic functions to death. Go ahead and do that. Here, I tell you what. Let me do it on Wolfram. Although, you probably should do it along with me on your calculator. Because this question is really a calculator than it is to do anything else. But I will plot them also. What were they? 36 over x and 36 over x squared. So, y equals 36 divided by x raised to the 2. And I wonder if I can do this. I'm not sure I can do this on Wolfram alpha. Y equals 36 divided by x. Let's see what we get. Yeah, we did do it.
Yep,
That's what mine looks like.
Okay, the blue line is the x squared part. Those are in quadrants 1 and 2 because y can never be positive if it's 36 over x squared. And the purple part, notice the difference in the first quadrant between the blue and the purple. The blue comes in deeper. It's because x is being squared. So this becomes a smaller number as x increases. When you put 36 over x squared, that's going to be a smaller number than 36 over x as x gets bigger. So it's worth noting that the blue is underneath the purple as long as we're greater than 1. All right. Find and compare the average rates of change of each function between x and 6. Okay. Rates of change. Rate of change is going to be f of 6 minus f of 1. That's the rise over the run. In other words, rate of change is slope.
Right.
And this is another preliminary to calculus because that's what differential calculus is all about, is instantaneous rate of change. Well, here they're asking you for the average rate of change. Now, when I look at a function, the average rate of change, I'm looking at 36 over x. Well, what is f of 6? If f of x, which it is 36 over x, what is f of 6?
36 over 6.
Okay, so if there's 6 on the x-axis, so that would be 6 also. In other words, f of 6 is 6. So that's 6. What is f of 1?
30, or just be 36.
It's that point right there, which is 36. So I want the difference in the y value, which is 6 minus 36, divided by the difference in the x value, 6 minus 1. So I have minus 30 over 5 minus 6 is the average rate of change. Now, how did I get minus? notice that the average rate of change is smaller. As x gets bigger, y gets smaller. So they're really talking about the slope of that line right there, and that has a negative slope. So we would expect to get a negative number. But how did we get a negative number? Well, you always have to put, it's always f of a minus f of b all over a minus b. And you can't switch these around. So I had to do f of 6 minus f of 1 all over 6 minus 1. I could not do f of 1 minus f of 6 all over 6 minus 1. And as long as I do it in this order, I'm going to get the right sign on the average rate of change, the slope.
Okay.
Okay, let's look at the function g of x, which is 36 over x squared. So now tell me what the average rate of change is. It's, I'll give you a start, g of something over what?
G, over x.
It's the change in y divided by the change in x. So the change in x, they're said from 1 to 6.
Okay.
What is g of 6?
It would be, well, if it's 6 minus 6.
Hold on. This is g.
Right.
What is g of 6?
Oh. It's 36 over 6.
So it's 1.
Okay.
So what is g of 1?
Just 36.
So there's our average rate of change for the g function, which is minus 35 over 5, so that's minus 7. So the g function has a greater rate of change, average rate of change, than the f function from 1 to 6. Now let's find out from 12 to 6 what their various rates of change are. So let's do the f first. The f function is 36 over x. So when I go from 6 to 12, what's my average rate of change going to be? Let's set it up as a general equation first. What goes in these parentheses?
It would be, it'd be 6 to 12, wouldn't it?
Well, that's fine to do it that way, as long as you do it that way in the bottom also. Or, same thing is f of 12 minus f of 6 all over 12 minus 6.
Okay.
This is fine. What's f of 6?
That would be 36 over 6.
What's f of 12?
36 over 12.
This is 3 over negative 6, so this is negative 1/2. So the rate of change in this hyperbola really got drastically less. notice they're saying the rate of change from 1 to 6 was a -6, and the rate of change from 6 to 12 is -1/2. Well, that's the first one is the slope of that line. The second one is the slope of that line. This slope right here is -1/2. This slope right here was -6. So
Okay.
that's really what they're attempting to point out here, is that the rate of change changes drastically on a hyperbolic function when you go from 1 to 6 as opposed to whether you go from 6 to 12. Y changes much faster when you go from 1 to 6 than it does when you go from 6 to 12, is what they're basically saying.
Right.
All right. What next?
All right, that's it on the homework, but I have a couple questions because we're going to have a quiz tomorrow.
Okay.
So let's see. The quiz is on, I don't know if we have time just to go over each one of these. Direct variation, inverse variation, fundamental theorem of variation, and graph of linear direct variation.
What's the equation for direct variation?
Let's see. I have it somewhere.
Well, better you try to remember it.
Okay, y.
Because you're not going to be able to look it up in your book on the test, right?
Right. Yeah.
Okay. So let's see if we can memorize it and have it make sense so that we can keep it in memory. It's either k over x or k times x. Which is it?
K times x.
Okay. That makes sense, right? Direct means that when x goes up, y goes up.
Okay.
When x
Yeah,
goes
that makes
down,
sense.
y goes down. Okay? So inverse variation must be the other one, which is what?
It's k divided by x.
Okay. Makes sense. Inverse divided by. In this case, when x goes up, y goes down. That's why it's inverse. When
Right.
x goes down, y goes up. So that's where it gets its name. The graph of a direct variation is a linear graph. It's a straight line and it always goes through 0. It might do that, might do this. In other words, it could have a different slope, but it always goes through 0 and it's always a straight line. In other words, try some various k's. If we plotted y equal 2x, that's just goes through the origin and has a slope of 2. If I plotted y equal 1/2 x, a different k, still goes through the origin, has a flatter slope. So direct variation always plots as a straight line through the origin.
Okay.
Inverse variation. How does that graph? It's what we've been doing all night. Is graphing y equals some number divided by x.
Okay, so it's the parabola or the
Hyperbola. So this is the way a standard hyperbolic function looks. By standard, I mean this with any value of k you want to put in there. Different k's will cause this to be flatter or steeper, but they all look like hyperbolic functions.
Okay.
Okay? So, well, does that answer You asked about direct variation, inverse variation, and the graphs of each.
Yeah, it says the fundamental theorem of variation and graph of linear direct variation.
Okay.
So is that what that is, just the graphs?
Yeah, in other words, if they were to show you graphs and they were to say, is that direct variation, it would depend. If it's a straight line and it goes to the origin, yes. If it's
Okay.
this, that is not direct variation because it doesn't go through the origin. It's a straight line, but it doesn't go through the origin.
Okay.
Okay, so for direct variation, it's got to be linear, meaning straight line, and go through the origin. To be inverse variation, it has to have vertical and horizontal asymptotes of 0, and be hyperbolic. In other words, not only does it have to be hyperbolic, but it has to be this. If I were to graph k over x minus 1, I don't think that qualifies. You would not be able to say that y varies inversely with x. It doesn't. It varies inversely with the quantity x minus 1.
Okay. Yeah, I get those again. I thought I was kind of confused, but
Well,
we
and
definitely
if I
went
have
over that.
something like this, I could say y varies inversely with the cube of x. Or the ones they've been giving us all night, this is y varies inversely with the square of x. So it doesn't always have to be just linear in the denominator. Here, if it was that right here, y varies directly with x squared. No, which takes away everything I said about this, makes it wrong. Do they address that here? The only thing they talk about here is varying directly with that's something I'm not positive about. Whether or not, if you can still have direct variation to a nonlinear variable, just like you can have inverse variation. Remember last week I told you that the force of gravity between two planets varies inversely with the distance between the planets, squared. It actually varies inversely with the square of the distance between the planets. So I know you can have inverse variation with a square in the bottom, and I'm 95% sure that you can have direct variation with a square in the top, which would mean it wouldn't be a straight line. If I had y equal kx squared, it would look like this. It would look like a parabola. And that could still be direct variation. So I'm not quite sure that one can make a statement about the graph of something that is directly or inversely varied. because if it was x cubed, the graph would look like this. So I'm not real sure how to answer the graphic part of your question.
Okay.
At this level, I'm thinking that they're only going to be dealing with linear variations. Tonight, well, they kind of dealt with x squared. In other words, they dealt with this one. It's just that that's somewhat hyperbolic, but not really. That's not really hyperbolic there. It's half hyperbolic, but it's not really hyperbolic. Hyperbolic is in diagonal quadrants.
Right.
All right. What else did you have?
I'm pretty sure that was it.
Okay.
It was direct variation, inverse variation, and the fundamental theorem of variation and graph of linear direct variation. Yeah.
The fundamental theorem of variation and graph. We'll try looking that up on this PDF here after we're off. Maybe you can find that fundamental theorem. Is this all Chapter 2 or some Chapter 1?
I think there may be some Chapter 1.
There's some Chapter 1. You might be able to find the answer to that directly in their theorem. I don't see their theorem anywhere here, but I'm looking at this big idea right here. It's not terribly important. I will say that. What's terribly important is that you memorize that that means direct and that means inverse. That's what's important that you know. Now, it is certainly possible to be inversely variation with the square of x, and it's possible to be directly variated with the square of x. So I'm not quite sure what that says about their graphs, but all right.
All right.
Well, let's see. Here, before you go, you asked about this last time, and I think I gave you the wrong answer when I went back and looked. Hold on. Let's see. You had a $48 credit going into tonight, so now you have a $16 credit.
Okay.
I think I missed one appointment when I was telling you last time. I didn't have one in here, but I went back and did a full accounting on it. So, okay? All right. Talk to you next time, Thomas. Yep.
Okay, sounds good.
Okay. Bye-bye.
All right, thank you.
Sure.